The Big Bang. What it is, and everything you need to know about the theory. What happened during the Big Bang? The Big Bang, according to modern cosmological theories, refers to the event that allowed the formation of our universe from an extremely dense and hot point, much like the singularity found at the center of black holes. The universe started from this singular point and has evolved to its current state. The exact size of the universe is unknown. However, we know that the observable universe has a diameter of about 93 billion light-years. How was the Big Bang discovered? Albert Einstein in 1915 radically changed our understanding of space and time with his general theory of relativity, which initially showed that the universe could not be static. At the time, there were no observations to support the expansion or contraction of the universe, prompting Einstein to introduce a cosmological constant into his equations to counteract gravity and maintain a static universe. Edwin Hubble's discovery in 1929 that the light from galaxies in every direction is red-shifted was a turning point. According to the Doppler effect, the wavelength of light from an object increases as it moves away, making it appear red. Conversely, as an object approaches, its light shifts towards blue. Hubble's observations were the first to suggest that the universe was expanding. Belgian priest Georges Lemaitre in 1927 proposed that if we were to trace the universe's expansion backwards in time, it would converge at a single point. The Big Bang theory faced opposition from the steady-state theory proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle. According to this theory, as objects moved away from each other, new objects were continuously formed, keeping the universe's density constant, and thus it had no beginning or end. The discovery of the cosmic microwave background radiation in 1965 provided strong evidence in favor of the Big Bang, as did the distribution of matter in the universe. Observations, including those of type I supernovae today, indicate that the universe is expanding at an accelerating rate, which is counterintuitive. Imagine throwing a ball upwards, which instead of slowing, speeds up as it ascends. While the Big Bang theory is the most accepted model in cosmology, it is not without flaws. Its biggest weakness is the inclusion of an initial singularity, which scientists believe results from the theory's classical, non-quantum nature. They anticipate that a quantum theory of gravity could resolve this issue. Moreover, the Big Bang theory does not sufficiently address issues like the horizon problem, the flatness problem, and the monopole problem. Common misconceptions about the Big Bang. Where does the name Big Bang come from? The term Big Bang suggests a massive explosion, but the Big Bang was neither big nor an explosion in the conventional sense. The term was coined mockingly by Fred Hoyle during a radio broadcast in an attempt to discredit the theory, as he supported the alternative steady-state theory. Although it initially caught on in popular science and the media, it was not widely used in academic literature until much later. The Big Bang is not an explosion, it's an expansion. While it might seem appropriate to compare the Big Bang to an explosion due to the intense heat and outward scattering, this comparison is flawed. The Big Bang did not scatter material into existing space. Space-time itself began to expand from that event. The Big Bang theory does not concern itself with the universe's beginning. The Big Bang theory does not deal with the origin of the universe, but rather with its evolution from the Planck time onwards, similar to how the theory of evolution concerns the development of life, but not the origin of life itself. Under general relativity, as we approach Tomorrow, the equations break down, meaning that classical physics cannot describe conditions at the Big Bang or earlier. The theory most compatible with our current understanding is the cosmic inflation theory, which provides a broader context for the early universe. The Big Bang is not an explosion, it's an expansion. At this point, you might think the term Big Bang is apt because the universe began in an extremely hot state and spread outward. Indeed, when a bomb explodes, it sends shrapnel and energy radiating outward from the center. However, although matter at high temperatures was dispersed from a central point during the Big Bang, this event was not chemical in nature like a bomb explosion. Nothing was scattered around because the space-time continuum itself was just beginning to form. Thus, the Big Bang was not an event occurring in a specific place. It was the moment when the fabric of space-time, which we can think of as a place, began to emerge. The Big Bang is not a location, it is a moment, a temporal event. Consider this. The Big Bang did not occur within space. The very thing that began to be produced during the Big Bang was space itself. Therefore, the universe did not start expanding within space. Space began expanding in all directions, and we are now within that expanding fabric. The Big Bang does not concern itself with the beginning of the universe. The Big Bang theory actually does not deal with the origin of the universe. It focuses on the evolution of the universe from the Planck time onward, similar to how the theory of evolution is concerned with how life evolved to its current state, not how life began. The general theory of relativity, which best describes the structure of space and time today, breaks down at T0. Therefore, general relativity alone cannot tell us anything about the origin of the universe. We need more than the classical Big Bang model to understand the moment of the Big Bang and what preceded it. The most robust candidate for this theory is currently the cosmic inflation theory, which is not our main topic here. The universe is not expanding into anything. One of the most common questions about the Big Bang and the universe is, what is the universe expanding into? The answer: nothing. The expanding entity is not matter within the universe, it is the universe itself. This answer may not seem intuitive to many people because, in everyday life, the expansion of something typically requires space in which to expand. However, this isn't applicable to space itself. The reason the expansion of the universe feels counterintuitive is that we tend to think of the universe as if it were a physical object that can be observed from the outside. If we consider the universe from within, there's nothing counterintuitive about its expansion. Imagine yourself as a creature living within the two-dimensional page of a book, as previously mentioned. From this perspective, the expansion of the universe doesn't feel counterintuitive. However, when you attempt to view it as an external observer might, that's when discrepancies arise between your intuition and how the universe expands. The problem here is the concept of looking at the universe from the outside, because to do so would require there to be an outside to begin with. But there isn't one, as the universe encompasses all of space. Therefore, questions about what the universe would look like from the outside remain meaningless. And if you try to understand expansion from within the universe itself, you will find it intuitively straightforward. What is the evidence for the Big Bang theory? The Big Bang theory, like all robust scientific explanations, is supported by a vast array of scientific data and findings, which help explain why and how the natural laws contained within it operate as they do. The observational evidence supporting the Big Bang theory includes the following. Darkness of the universe. The universe is a very dark place. At night, even planets are shrouded in darkness. If the universe were infinite, it would contain an infinite number of stars and an infinite amount of light. Therefore, it would not be dark. Thus, the universe must be finite. If it is finite, it must have a beginning. Redshift of light. from distant galaxies. The light spectrum from more distant parts of the universe shifts towards the red end. This phenomenon is known as redshift. It indicates that these regions are moving away from us, supporting the idea that the universe is expanding from an initially dense state. Uniformity of the universe. There is no evidence to suggest that any part of the universe is special. The universe appears homogeneous and isotropic at large scales. No matter where you look, the universe has similar properties, which indicates that it looks the same in every direction. These points of evidence are key in supporting the Big Bang theory and help illustrate the model's effectiveness in explaining the observations and phenomena we can measure in the cosmos.